In the early 1990s, the Powder River Basin was asking locomotives to do something brutal, lift mile-and-a-half-long coal trains out of Wyoming, fully loaded in dust, snow, rain, and on rail that was often anything but clean. Each train could weigh well over 15,000 tons. At the head end, diesel engines thundered, generators loaded, traction motors pulled, and steel wheels tried to bite into steel rail with a contact patch smaller than your hand. If you want to see how industrial battles like this are really won, subscribe to Industrial Empire. Just listen to a heavy coal train starting under load. The obvious answer seems simple: add more horsepower. Bigger engines, more cylinders, more fuel, more noise. But the Powder River Basin exposed a harsher truth. A locomotive can only pull as hard as its wheels can grip the rail. Once those wheels start slipping, extra horsepower does not become more pulling force. It becomes heat, wear, alarms, and lost momentum. That was the real limit hiding underneath the horsepower race. For decades, EMD had dominated American freight with reliable diesel-electric locomotives, while GE kept pushing for a larger share of the market. By the 1990s, both builders understood that coal service was the proving ground. Whoever could start heavier trains with fewer locomotives would win real money for the railroads. The coming fight would not be decided only inside the diesel engine. It would be decided in milliseconds at the railhead by electronics sensing the first hint of wheel slip and correcting it before the train lost its grip. That is where AC traction changed everything. The steel wheel on a locomotive looks massive, but the part doing the actual work is almost absurdly small. Where that wheel touches the rail, the contact patch is roughly the size of a coin, or at best a few fingertips spread across a strip of polished steel. That tiny patch has to transmit everything: the force to start the train, the force to keep it climbing, and the braking force to stop it again. The locomotive may have thousands of horsepower behind it, but the rail only accepts as much torque as friction will allow. Steel on steel is efficient because it rolls with very little resistance. That is why a train can move incredible tonnage once it is underway. But the same low resistance becomes a problem when the locomotive needs grip. A rubber tyre deforms and bites into pavement. A steel wheel does not bite much at all. It depends on clean contact, steady weight, and precise control. The real world makes that contact patch worse. Rain puts a film of water between wheel and rail. Snow and ice reduce friction even further. Dust from coal loading, rust, leaves, grease, and oil can turn the railhead into a contaminated surface. On grades, the problem grows because gravity is pulling the entire train backward while the locomotives are trying to drag it forward. If the traction motors apply just a little too much torque, the wheel begins to rotate faster than the locomotive is actually moving. That is wheel slip. In that moment, the locomotive is no longer converting power into pull efficiently. It is polishing the rail, wearing the wheel, and risking damage to the traction motors. Older control systems had to respond by cutting power. That protected the machinery, but it also reduced tractive effort at the worst possible time, during a start, on a hill, or with slack running through a long train. The crew could have plenty of engine horsepower available, yet still be forced to back away from it because the wheels could not hold. This is why adhesion, not horsepower, became the hidden battlefield. The winning locomotive would not simply be the one with the biggest diesel engine. It would be the one that could sense the edge of slip, ride that edge, and recover instantly when conditions changed. So the central question became, how could builders push closer to the limit of adhesion without crossing it? A diesel-electric locomotive is not a giant truck with a gearbox hiding underneath. The diesel engine does not send power through a drive shaft to the axles. Its main job is to spin a generator, or in later designs, an alternator. That distinction matters because the locomotive is really a mobile power plant. The diesel engine, called the prime mover, burns fuel and produces mechanical horsepower at its crankshaft. That rotating energy is converted into electrical energy, then routed through control equipment to traction motors mounted down near the axles. Those traction motors are the parts actually turning the wheels. On many freight locomotives, each axle has its own motor geared to it. When current flows into the motor produces torque. That torque passes through gears into the axle and the wheel pushes against the rail. So when a railroad bought a locomotive rated at 3,000 horsepower or 4,000 horsepower, that figure described what the diesel engine could produce under ideal conditions. It did not automatically mean all of that power became useful pull at the rail. The useful pull is tractive effort. That is the force the locomotive can apply to the train through the coupler. At low speed, especially when starting a heavy train, tractive effort is the number that matters most. Horsepower tells you how much work the locomotive can do over time. Tractive effort tells you how hard it can pull right now. This is why two locomotives with similar horsepower could behave very differently in service. One might look impressive on a specification sheet, but struggle to put its power down without slipping or overheating. Another might use the same basic diesel output more effectively because its electrical system and traction control could feed the motors with finer control. For decades, the standard answer was the DC traction motor. DC motors were rugged, familiar, and well understood. Railroads knew how to maintain them. Builders knew how to package them, and they had powered generations of successful locomotives. But they also came with limits. At low speed and high current, they generated tremendous heat. Their commutators and brushes were wearing parts. Their ability to keep applying maximum torque was constrained by temperature, flashover risk, and the control systems around them. That is where the next revolution begins. The fight was not just over making more horsepower. It was over building a traction system that could turn that horsepower into controlled force at the rail, for longer, with less drama. The classic DC traction motor earned its place because it was a practical machine for a brutal job. Inside it, electricity flowed into a rotating armature, and the magnetic fields inside the motor turned that armature into torque. That torque then went through reduction gears to the axle. The key physical parts were the brushes and the commutator. The brushes were usually carbon blocks held against a rotating copper surface. The commutator was built in segments, and as the motor turned, it switched current through the armature windings at the right moment. In simple terms, it kept the magnetic push happening in the correct direction so the motor continued to rotate. That system was not delicate laboratory equipment. It could survive vibration, dirt, weather, rough track, and long service days. Railroad shops understood the parts, stocked the spares, and trained mechanics around them. If a brush wore down, it could be inspected and replaced. If a commutator needed attention, it could be cleaned, cut, or repaired by people who already knew the craft. For builders, DC traction was also economical. The technology was mature, the control equipment was proven, and the risks were known. A railroad buying locomotives in large numbers did not want an experiment under every car body. It wanted machines that could be diagnosed quickly and returned to service. But the very parts that made DC motors understandable also created limits. At low speed, a heavy freight train demands enormous current. The motor is turning slowly, airflow is limited, and heat builds up in the windings, brushes, and commutator. The locomotive may have plenty of engine horsepower available, but the traction motors can only absorb so much current before temperatures climb into dangerous territory. There was also flashover. If conditions around the commutator became severe enough, electricity could arc across where it was not supposed to go. That was not just inefficient, it could damage the motor and take the locomotive out of service. The harder the motor was pushed at low speed, the more attention these risks demanded. Maintenance followed the same pattern. Brushes wore, commutators needed inspection, carbon dust, heat, vibration, and electrical stress all left evidence. DC traction was reliable because railroads stayed on top of it, not because it was free of wear. The result was a system that could start heavy trains and serve for decades, but not without a ceiling. Heavy haul railroading did not need a locomotive that could produce one heroic burst of pull and then back off. It needed sustained, controlled force at walking speed, where heat, current, adhesion, and motor limits all collided. That was the opening AC traction would exploit. Focus on one powered axle under a heavy locomotive. The diesel engine and generator are sending electricity into the traction motor, the motor is twisting through the gears, and the wheel is trying to push backward against the rail. The rail pushes forward in return. That small contact patch, roughly the size of a coin, is where thousands of horsepower becomes motion. At first, the wheel rolls cleanly. Its rotation matches the locomotive speed, and the steel surfaces grip through adhesion. But as torque rises, the contact patch approaches its limit. Add rain, oil, leaf residue, frost, or just a tiny change in rail condition, and the wheel can cross the line. It starts turning slightly faster than the locomotive is actually moving. That is wheel slip, not a dramatic burnout like a car at a drag strip, at least not at first. It can begin as a small difference between wheel speed and ground speed. But once the wheel is sliding instead of gripping, adhesion falls. The motor may still be applying power, but that power is no longer being turned efficiently into pulling force. It is being wasted as heat, vibration, and polished rail. Conventional control systems had to detect that slip after it had already begun. They watched for signs like one axle accelerating faster than the others or a sudden change in motor current. Once the system knew an axle was slipping, it responded by cutting power to bring the wheel back under control. That sounds reasonable until you remember that a road freight locomotive has 6 powered axles. Each axle is seeing slightly different rail conditions. One wheel set may be on clean dry steel while another passes over moisture or contamination. So the locomotive is constantly testing the edge, losing grip, backing away and trying again. Every time that happens, usable horsepower arrives in pulses instead of a steady shove. The locomotive may have the engine output on paper, but the rail only accepts the portion that the wheels can apply without breaking loose. The rest disappears into correction cycles. The real prize was not simply more horsepower. Railroads already knew how to build powerful locomotives. The prize was control, keeping each axle as close as possible to the limit of adhesion without stepping over it. What if a locomotive did not have to wait for slip, panic and retreat? What if it could hold every wheel set right at the edge? The answer was not a bigger diesel engine. It was a different way of controlling the electricity after the engine had already made it. In an AC locomotive, the diesel still turns an alternator. That alternator still produces electrical energy. But instead of feeding that power straight into DC traction motors in the old way, the locomotive sends it through power electronics. Rectifiers and inverters reshape the electricity into controlled 3-phase AC power for the traction motors. That detail changed everything. AC traction motors are rugged, simple machines compared with DC motors. They do not need the same brushes and commutators carrying heavy current through moving contact surfaces. But the real breakthrough was not just the motor. It was the inverter sitting between the alternator and the axle, with microprocessors telling it exactly what to do. Those microprocessors could adjust voltage and frequency many times per second. Frequency helped determine motor speed. Voltage helped control the magnetic force inside the motor. Together, they allowed the locomotive to regulate torque with a level of precision older systems could not match. Now the control system was not just reacting to a wheel that had already slipped badly. It could constantly compare axle behavior, motor speed, commanded torque, locomotive speed, and electrical feedback. If one axle began to creep toward the edge of adhesion, the computer could trim torque almost instantly, then feed it back in as soon as grip returned. That made the locomotive feel less like 6 axles being managed as a group and more like 6 individual machines negotiating with the rail. Each axle could be kept closer to its own limit instead of forcing the whole locomotive to back away because one wheel set had found a bad patch of steel. This is why AC traction can sound almost magical in railroad discussions. But it was not magic horsepower. The prime mover was not suddenly creating free energy. A 4,000 horsepower locomotive was still working with roughly 4,000 horsepower from the engine minus normal losses. The difference was how much of that power could actually become tractive effort at the rail. The adhesion numbers tell the story. Older DC systems often operated around 18 to 20% adhesion in heavy service. Modern AC systems, under demanding conditions, could approach the high 30% range. That does not mean every locomotive always reached those figures, but it shows the scale of the leap. For railroads, that leap mattered more than a brochure number. Better adhesion meant heavier trains from a stop, stronger low-speed pulling, fewer correction cycles, and less wasted power. AC traction turned electronics into grip, and grip was exactly where General Electric was about to hurt EMD the most. The crucial shift was that wheel slip stopped being treated as a simple failure. On an older system, the ideal was to keep the wheel from slipping at all. If it did slip, the control system reduced power, waited for the wheel to recover, and then tried again. That protected the motor and the rail, but it also meant the locomotive was always stepping back from the very edge where maximum pulling force lived. AC traction changed the target. Each axle had speed information coming back to the control system. The locomotive could compare those axle speeds against each other, against the expected train speed, and against the motor commands being sent through the inverter. When one wheel set began to move slightly faster than the locomotive itself, the software could see the difference almost immediately. And here is the counterintuitive part. A tiny amount of slip can create more grip than a perfectly rolling wheel. The goal was not a wheel spinning wildly on polished rail. That destroys adhesion, heats metal, wears wheels, and can damage traction motors. The goal was controlled creep, a microscopic difference between wheel speed and ground speed, held inside a narrow, useful zone. The control system could let the wheel flirt with that edge, trim torque before it ran away, then restore torque as conditions improved. That required more than a single reaction. Rail conditions change constantly. One axle might pass over damp rail while another is still on dry steel. A curve can change loading from side to side. A heavy pull can shift weight across the trucks. Even the unloading of an axle under torque matters, because less weight on the wheel means less available adhesion. The AC locomotive software could account for those changes in real time. It did not assume every axle had the same grip. It watched each one individually and adjusted torque to match what that axle could actually use at that instant. For crews and railroads, the results showed up in the hardest moments, starting a heavy train, dragging tonnage up a grade, or pulling slowly where diesel horsepower is plentiful but adhesion is scarce. Instead of blasting sand and repeatedly cutting power, the locomotive could stay hooked up with each axle working close to its limit. This was the conceptual breakthrough that made AC traction so disruptive. It turned slip from an enemy into a measured tool. So if this technology was powerful enough to change the rules of freight railroading, the next question is obvious. Who brought it to American freight first? The answer was not General Electric, at least not at first. The first real North American freight test of modern AC traction came from EMD, working with Siemens. In 1992, EMD built 4 experimental locomotives called the SD60 Mac. They looked like a branch of the familiar SD60 family, but underneath they carried the equipment that mattered: Siemens AC traction motors, inverter controls, and a 4,000 horsepower diesel engine driving the whole package. Burlington Northern became the proving ground. That detail matters because this was not a laboratory demonstration on perfect rail. Burlington Northern had coal trains, mountain grades, bad weather, long consists, and the kind of low-speed heavy pulling where adhesion decides whether a locomotive is useful or just impressive on paper. The 4 demonstrators went into service where AC traction could be judged harshly. They had to start heavy trains without wasting power in wheel slip. They had to keep pulling at slow speeds where DC traction motors could overheat. They had to show that individual axle control was not just clever electronics, but a practical advantage for a railroad trying to move tonnage. And they did. The SD60 Max proved that AC traction could change the economics of heavy haul. A locomotive that could apply more of its horsepower to the rail at low speed could do work that previously required more units, more sand, more patience, or all 3. It was not only about peak horsepower, it was about how much of that horsepower could actually become tractive effort when the train was heavy and the grade was unforgiving. For Burlington Northern, the test was convincing enough to lead directly to the production SD70 Mech. That model kept the same basic promise, but turned it into a road locomotive a major railroad could buy in large numbers. Burlington Northern placed major early orders, especially for coal service, and after the Burlington Northern and Santa Fe merger, the orange, green, and later heritage-coloured AC units became a defining sight in Western coal country. The SD70 Mac was not a minor experiment that slipped into the catalogue. It became one of EMD's most important modern locomotives, with more than 1,400 sold. It proved that EMD had not missed the idea of AC traction. In one crucial sense, EMD helped open the door. But that is the twist in the story. EMD demonstrated the technology, validated it under brutal freight conditions, and turned it into a successful production locomotive. Then General Electric walked through that same door and built the larger empire on the other side. General Electric did not answer EMD with a science project. It answered with a locomotive railroads already knew how to understand. That locomotive was the AC 4400 CW, introduced in the early 1990s and delivered to customers beginning in 1994. On paper, the headline was simple: 4,400 horsepower, wide cab, 6 axles, and AC traction for heavy freight. In practice, it was the machine that let GE turn a breakthrough into a fleet purchase. The key was what GE changed and what it did not change. Under the hood sat the familiar 7FDL 16 prime mover, a 16-cylinder engine that was already part of GE's freight locomotive story. The car body, cab layout, control stand, and general maintenance world all grew out of the -8 and -9 lineage. To a railroad mechanical department, the AC 4400 CW did not look like a strange new animal. It looked like the next step in a family they were already buying. But beneath that familiar shell, the traction system was different in the way that mattered. The locomotive used 6 AC traction motors, one on each axle, fed by inverter equipment that allowed the controls to manage power with much finer precision than older DC systems. Instead of relying on a cruder battle against wheel slip, the locomotive could constantly adjust how each axle used available adhesion. That made it especially valuable in the work railroads cared about most: starting heavy trains, grinding up grades, and keeping tonnage moving at low speeds without cooking traction motors. This was the commercial genius of the design. GE did not ask railroads to bet everything on a completely unfamiliar platform at the exact moment it was asking them to adopt new traction technology. It packaged AC traction inside an architecture that had already been gaining trust. The risk felt smaller, even though the performance step was large. For dispatchers and operating departments, that mattered as much as the engineering. A locomotive that could replace more DC units in heavy service was not just a better machine. It could change train planning, helper requirements, fuel use, and locomotive assignments. The AC 4400 CW was not marketed only as a technological upgrade. It was a tool for moving heavier trains with more confidence. Early customers showed where the market was going. CSX bought the model for demanding eastern coal and mountain service. Union Pacific also became a major buyer, using AC power across a vast system where grades, heat, and long heavy trains punished anything marginal. By the mid-1990s, GE had a locomotive that did exactly what the moment required. It carried revolutionary traction equipment, but it arrived wearing the face of an increasingly trusted GE road engine. That combination turned AC traction from a proving ground success into a purchasing strategy. Inside the AC 4400 CW, the real revolution was not just the traction motor, it was the control system wrapped around it. Older DC locomotives could be strong, but they were limited by the way power was switched, measured, and corrected. The AC system needed high-power semiconductor switches that could take the generator's electrical output and chop it into precisely controlled three-phase power for the traction motors. Those switches lived inside inverter cabinets, and they had to survive huge currents, constant vibration, dust, heat, and railroad maintenance reality. Cooling was just as important as the electronics. An inverter that overheated was not a breakthrough, it was a failure waiting on a grade. So the locomotive's power electronics used serious thermal management, with cooling systems built to keep the semiconductor hardware within safe limits while the locomotive pulled at low speed for long periods. That was where AC traction proved its value, not in a brochure, but with a heavy train moving slowly while the electrical system stayed under control. The motors themselves were simpler in the places railroads cared about. AC induction motors had no brushes and no commutators, two wear points that DC traction motors carried as part of daily life. That reduced traction motor maintenance and made the motors better suited to sustained high current work at low speed. In coal service, mountain service and drag freight that mattered more than a flashy top speed. The other half of the machine was the brain. Axle speed sensors watched every axle for the first signs of slip. Microprocessors compared those signals, adjusted inverter output, and coordinated the locomotive's response faster than an engineer could react by hand. Instead of waiting for wheels to break loose and then recovering, the system tried to stay right on the edge of adhesion, where the locomotive was pulling as hard as the rail would allow. That made diagnostics part of the product, not an afterthought. The locomotive could monitor faults, record events, and help shop crews find problems in the traction system instead of chasing symptoms. For railroads buying hundreds of units, that kind of information could save time across an entire fleet. GE and the industry also looked beyond the electrical cabinet. Better trucks, high adhesion truck designs, and steerable truck concepts all attacked the same problem, turning locomotive weight into usable pull without wasting it in wheel slip or rail wear. The AC 4400CW belonged to that broader shift. It was not merely a diesel engine feeding different motors, it was a rolling computer using sensors, software, inverters, cooling, and mechanical design to make 6 axles behave like a coordinated traction system. The payoff for all of that technology showed up in a simple railroad question. How much train can this locomotive actually move? Horsepower could make 2 locomotives look equal on paper. A 4,400 horsepower AC unit and a 4,400 horsepower DC unit were both converting diesel fuel into mechanical output. But railroads did not buy locomotives to win spec sheet arguments. They bought them to start loaded trains, climb grades and keep schedules without burning money. The difference was tractive effort, especially continuous tractive effort at low speed. Starting tractive effort is the big shove that gets a train moving. Continuous tractive effort is what the locomotive can keep producing without overheating traction motors or losing control of the wheels. That second number was where AC traction changed the math. A DC locomotive could pull hard, but sustained low-speed work punished its traction motors. High current through DC motors created heat, and heat set the limit. If a heavy train crawled up a grade for too long, the locomotive could not simply keep asking for maximum effort forever. The equipment had thermal boundaries. An AC locomotive could manage that low-speed, high-current zone much better. Its induction motors and inverter controls allowed the locomotive to keep applying strong, controlled torque while the train moved slowly. That meant the same horsepower could translate into more usable pull during the part of the trip that mattered most. This is why the revolution was most visible in coal, ore, grain, potash, and mountain railroading. Those trains were not about sprinting across flat territory at passenger train speeds. They were long, heavy, and often slow. A loaded coal train grinding through Appalachia, a mineral train in the west, or a potash train fighting grades needed locomotives that could live in the hard pull zone without constant wheel slip or overheating. In that world, one AC unit could sometimes do work that required more than one older DC unit, not because it had magic horsepower, but because it used its weight and electrical system more effectively. If a railroad could replace 3 units with 2 on a certain assignment, the savings reached far beyond the fuel tank. Every locomotive removed from a consist meant 1 less diesel engine to feed, inspect, service, and eventually overhaul. It meant fewer traction motors exposed to wear, fewer air compressors, fewer cooling systems, fewer brake components, and fewer fault opportunities. Across a railroad running hundreds of heavy trains, small changes in locomotive count became large changes in operating cost. It also improved train handling at the worst moments. Heavy trains are hardest to manage when starting on a grade, restarting after a stop, or moving through territory where adhesion changes under the wheels. AC control gave crews and dispatchers more confidence that a train could get moving and keep moving without doubling a hill or calling for helper power as often. But AC was not automatically the best answer for every train. Fast intermodal service had different priorities: speed, acceleration, route profile, locomotive availability, and fleet commonality all mattered. In some corridors, a DC unit could still be perfectly useful and cheaper to buy. That nuance is important, because the AC victory was not just a technology story, it was a business story. GE did not merely build a locomotive that was clever in engineering terms. It built a locomotive that changed the cost equation on the hardest, heaviest, most profitable work many railroads performed. By the time AC traction became the prize, GE had already spent years changing what railroads thought a GE locomotive could be. The older image of GE was not always flattering. Early U-boats and some later models had given certain railroads reasons to be cautious, but the -8 and -9 families helped rewrite that reputation. They brought better fuel efficiency, stronger onboard diagnostics, cleaner modular maintenance, and a growing record of reliability in daily service. That mattered because railroads were not buying a single experimental machine, they were buying fleets. A new locomotive order could mean hundreds of units, millions of dollars in parts inventory, new training programs, and years of mechanical department commitment. If the technology failed, the railroad did not just have a bad locomotive, it had a network problem. GE understood that the sale did not end when the locomotives left Erie. The company put field support people close to the railroads, especially on major fleets where early performance would shape future orders. GE technicians worked alongside railroad maintenance forces, helped interpret fault data, tracked recurring failures, and pushed fixes back through the engineering pipeline. That relationship changed the risk calculation. A railroad trying expensive new AC power did not have to feel like it was solving every problem alone. If traction inverters, control software, cooling systems, or diagnostic screens created new maintenance questions, GE had people in the field who could help turn those questions into procedures. The onboard computers were part of the same strategy. Diagnostics did not make a locomotive immune to failure, but they shortened the hunt. Instead of a shop crew chasing symptoms through a maze of wiring and components, the locomotive could point them toward fault histories, sensor readings, and likely trouble spots. Less guessing meant less downtime. GE also leaned into support arrangements built around availability. Railroads cared about whether a unit was ready when the dispatcher needed it, not just whether it looked impressive in a brochure. Contracts, parts programs, warranty structures, and technical support could all be shaped around keeping locomotives earning money instead of waiting in a shop track. This was where GE's approach became larger than horsepower, adhesion, or inverter design. It was selling confidence. It was telling railroads, if you commit to this new technology, we will help you keep it working. By the time AC traction matured, GE was not just offering a locomotive, it was offering a way to reduce the risk of changing the railroad itself. The next prize was not just AC traction, it was the promise of 6,000 horsepower in a single locomotive. On paper, the logic was irresistible. If a railroad could replace 3 older units with 2 stronger ones, it could cut fuel use, reduce maintenance, shorten locomotive consists, and put more power on the head end without adding more crews or more machines. For an industry obsessed with tonnage and asset utilization, 6,000 horsepower sounded like the next great efficiency leap. EMD answered with the SD90 May, built around the new 265H engine. This was a major break from the long-lived 710 series that railroads already understood. The H engine was larger, more complex, and pushed EMD into a new engineering era at the exact moment when customers were already adjusting to AC traction, new electronics, and new maintenance practices. That risk quickly became visible. The SD90 Mac fleet developed reliability problems tied to the new prime mover and its supporting systems. Some railroads found the locomotives too troublesome for the heavy service they had been bought to dominate. Instead of becoming the new standard, many units were stored, derated, rebuilt with more familiar engines, or treated as special cases inside mechanical departments. For EMD, the damage went beyond repair bills. Railroads had trusted the company for decades because its locomotives were familiar, durable, and easy to keep moving. The SD90 Mac challenged that image. A railroad could forgive teething problems on a small test order, but large fleets with chronic issues changed how future purchasing committees judged risk. GE was chasing the same dream with the AC6000CW, and it also ran into trouble. The 16-cylinder H engine used in that locomotive had its own reliability problems, and the 6,000 horsepower market never became the clean breakthrough that either builder had hoped for. This was not a simple story where one company made mistakes and the other did everything right. The difference was what each builder had beneath the experiment. While the AC6000CW struggled, GE could keep selling the AC4400CW, a more conservative 4,400 horsepower locomotive that railroads already knew how to use. It had enough power, strong AC adhesion, improving reliability, and a growing installed base across major North American carriers. That gave GE a safety net EMD badly needed. When the 6,000 horsepower idea lost momentum, GE did not have to depend on it. Railroads could step back from the high horsepower gamble and still buy large numbers of GE AC units that fit their existing operations. EMD, meanwhile, had tied too much of its comeback story to a locomotive that made customers nervous. The SD90 Mac was supposed to prove that EMD could match the new era on its own terms. Instead, it reminded railroads that the safest choice might no longer come from the company that had once defined safety. AC traction did not win the locomotive war by itself. It locked in a set of advantages GE had already been building for years. By the time heavy-haul railroads were ready to buy AC power in large numbers, GE was no longer the risky outsider it had been in the early -7 era. Its locomotives had become more reliable. Its customer support had improved, its production system could deliver big fleet orders, its financing arm could help railroads justify expensive purchases, and its newer units were arriving at the exact moment when coal, grain, and intermodal operators wanted better adhesion from every axle. That is where AC traction became so powerful commercially. It gave railroads a simple economic argument. A locomotive that could pull harder at low speed, reduce wheel slip, and keep heavy trains moving with fewer units was not just technically impressive. It changed train planning, fuel use, maintenance scheduling, and fleet utilization. For a railroad moving coal over mountain grades, the difference could show up every day. Better adhesion meant fewer stalls, fewer helper movements, and less wasted horsepower turned into heat and wheel wear. The purchase price was higher, but the savings were visible in the work the locomotive could actually perform. EMD was not absent from this story. The SD70 Mac was a serious and successful AC locomotive, especially on western coal routes. Burlington Northern became one of its most important customers, and the design proved that EMD could build a strong AC platform when the product fit the job. The problem was scale. GE spread its AC4400CW across more major carriers, in larger numbers, and with a platform that became familiar across the North American heavy-haul network. As railroads standardized around GE fleets, every additional order made the next one easier. Mechanics learned the systems, parts pipelines matured, dispatchers and train masters knew how the locomotives behaved, fleet managers could compare performance across thousands of units. That momentum mattered as much as the inverter cabinets and traction motors. Once a railroad had already built its operating practices around GE AC locomotives, switching back to EMD required more than a good sales pitch. It required proving lower risk, equal support, and better economics over the life of the fleet. So AC traction did not destroy EMD in one dramatic blow. It amplified GE's existing lead and gave customers a reason to keep extending it. The contest had moved beyond who built the best diesel engine. The new battlefield was electronics, software, adhesion control, and the ability to turn complex technology into dependable railroad tonnage. That brings us back to the coal train at the beginning. Two locomotives could have similar horsepower ratings on paper, but out on the rail, the winner was the one that could turn more of that power into controlled pull. AC traction made that possible by managing wheel slip instead of simply fighting it. The locomotive did not need a bigger diesel engine to become more useful, it needed better control at the contact patch between steel wheel and steel rail. EMD deserves credit in that revolution. The SD70 Mac helped prove that AC power could handle demanding heavy haul service, and on the right routes it became exactly the machine railroads needed. But GE turned the technology into a broader commercial weapon. The AC 4400CW arrived with the right horsepower, the right adhesion, and the right support network for railroads buying entire fleets. That is why the outcome was not decided by one spec sheet. It was decided by daily railroad math. How many units were needed on a train? How often a train stalled? How much horsepower was wasted as heat, noise, and wheel wear? How quickly a shop could diagnose a fault and return a locomotive to service? By the time railroads answered those questions at scale, GE had made itself the safer bet for modern heavy haul power. EMD had helped open the AC era, but GE built the platform that more railroads standardized around, so the war was won at the railhead. Not by the loudest engine and not by the biggest horsepower number, but by electronics, software, and controlled wheel slip. Thank you for watching. If you want a deeper episode on the SD70 Mac, the AC 4400CW, or the failed 6,000 horsepower race, write your pick in the comments.